Well, we have a really interesting situation where we're starting to put an awful lot of pressure on the center of this star. Now, you thought there was a lot of pressure when we were talking about fusion. Well, it gets worse, because depending on the mass of the star, we can actually burn helium, and in fact it happens when we start converting the core to carbon and oxygen. And then of course we have a helium burning shell, and then above that we have a hydrogen burning shell, which is hanging on for dear life. And then we have the rest of the star, which is pretty much exactly the same as when we started. It's hydrogen and helium mixed up together, depending on the metallicity of the star. So, something really interesting though happens to the core of this star. It doesn't stay the same. There's so much force. Remember our bowling ball. There's so much mass pushing down on the center of the star that the pressure, the gas pressure, actually can't deal with it. And we have a fundamental change happening in the star over its fusion lifetime, which is that the core, unfortunately, I'm sorry to tell you this, the core becomes degenerate. Yeah. We're now going to be talking about degenerates. So, basically the idea with this is that if you take a gas and you compress it, to a certain point, well, it depends on the gas. It's pretty easy. You're just pushing the molecules closer together, right? And it means that they're probably hitting each other more. It probably raises the temperature. That's fine. If you push them so closely together that the atoms themselves can now actually have trouble moving, and you start pushing so strongly that the very electrons that are orbiting around these atoms find themselves constrained. Which is quite amazing, because the electrons aren't that far away from the nucleus. Basically what happens, because you're familiar with a model of an atom, right? Classical model. We have a nucleus with protons and neutrons, and we have electrons orbiting around it, right? This is what we learned in school. Completely wrong. But I don't really understand the quantum version, so we're going to stick with it. Basically, well, don't feel too bad for me. I think a lot of, who was it that said, nobody understands quantum physics? Is that fine? That's right. I don't know who it was. Whoever it was spot on. Okay. Sorry. But these electrons, we're talking about them classically, they have different amounts of energy. They orbit at higher or lower orbitals. So they're flying at different distances from their nucleus. It's a horrible classical explanation. It's completely wrong, but that's okay. If you start pushing on these electrons, you force them down into lower and lower orbitals. You start filling up the lower energy states of the atom. Now, if you do this, that actually allows you to release more energy. It allows the pressure to push these things even further. You end up with a degenerate system. Now, that's what happens at the very center of our low-mass stars, in fact, all stars, as they do their hydrogen fusion. And in the end, what happens is that you actually get such a strongly condensed center that it actually has difficulty with the amount of energy that it's producing, holding on to its outer layers, and you start ejecting the entire envelope of the star. And you end up with this. Now you can see, I would turn down the lights, but I don't know how to turn them back up, so we're gonna leave them right there. You can see at the very center of this picture what's left. You can actually see the degenerate core of this star is still there, spinning. It's incredibly hot. It's no longer fusing. It's just cooling down. And it's just sitting there in space. It's radiating like crazy. It's really hot. And it's not getting any more energy. It's just getting colder and colder. So these things are beautiful, right? Pretty neat. So there's our star. That's what's left of it. This is another one. This one's a little bit harder to see. Now, the different colors are the different materials that were in the star, the different layers being shed as they're thrown out into space. Now, there's a reason for the shape of these clouds. I'm not going to get into it. It's really complicated. It has to do with magnetic fields. It has to do with the rotation of the star. It's pretty neat. They're beautiful. So where's our star? There's our star.
Andrew, is that where you get planetary nebula?
Thank you. That's right. Those objects that I just showed you were exactly planetary nebulae. It's another example of terrible naming in astrophysics. It has nothing to do with planets. The planets are long gone. Why did we not change it? Why didn't we make it A, B, C, D, E, F, G? You know, in a couple of years it would have been a bit awkward, but people would have got used to it, and then students coming in would have just known that system, and nobody would have talked about it. It would have been fine. Why did we call it planetary nebula? Who knows? But this is what happens in the center of our awkwardly named planetary nebula, a white dwarf. This is the end of a main sequence star evolution. It sits there, it radiates, it gets cooler and darker and quieter, and it just disappears. Pretty boring. That's why they call these stars, that's why they say that they reside in the stellar graveyard. They say these stars are dumb, you know, they're boring, they're dark, they're never going to do anything, they're never going to get any hotter, they're never going to get any bigger, they're never going to do anything interesting, let's just forget about it. Funnily enough, a very large percentage of the stars in the universe end up like this, which is interesting.
I think you have a question.
I'm just kidding. I've got something else to talk about, I'm sorry. That would have been terrible. I would have said, there's really fascinating stuff about degenerate low-mass stars, and I was like, let's go home. It's not the end of the story. Because most of the stars in the universe are not stars like our sun. Although I am talking about stars like our sun, I'm talking about the fact that most stars in the universe are in groups. So many stars are in binary configurations. Some are in systems with 3 stars. Some are in systems with 4, 5, 6, 7. And even more. I'm not going to count them all because we end up getting into open clusters which have thousands of stars. We end up getting into globular clusters which have tens, hundreds, maybe even a million stars in one group. Can you see that with the lights? Yeah? Yeah. Okay, so this is what is going to save our really boring degenerate white dwarf. And it's the fact that it's in a system with another star. So these white dwarfs are going to get there as long as they've got their friends around them, which is really, it's neat, it's uplifting, I like it. As you can see, this is why this stuff is so interesting. It's great. So, it's excellent. This is a picture of the Roche lobe. I'm sure I don't have to point that out to anyone. I had physics lecturers like this. They're like, there you go. Exams on Tuesday. Good luck with that. I'm going to explain this diagram. Because what do we have? Well, we have a degenerate star, and it's small, but it's really hot. And we have this star that has an incredible force of gravity. Okay? If you lined it up compared to a much bigger star that wasn't a degenerate star, that was just a normal star, a star that was a little younger, a really interesting thing happens. I'm going to explain that. That's what this diagram actually shows you. Because these stars have an amazing ability. And that ability is that they can actually pull mass off other stars to completely change the way that they're existing. So I'm going to draw a diagram here. I was practicing this last night. I'm terrible at drawing. I went through several iterations. We had things that looked like pyramids. We had, I was going to do it a lot of different ways. Here's the thing. Stuff with gravity has potential. All right? If you are standing on a cliff and you jump off, what happens? This isn't a philosophical question. It's not a theological question. What happens to you if you jump off the cliff? You're pulled down, right? And that's because the gravity of the Earth had a certain potential where you were, and you headed down because you were pulled towards the center of the Earth.